So now we're going to refer back to that tab data on page 138. And our goal now is to write an equation to represent these data. So the first thing we're going to introduce to is what's called the Y-intercept. And this is the point where the graph crosses the y-axis, meaning a y-intercept has the coordinate 0 for x and then some sort of number for y. It could be 0, it could be anything. So when we look at our table of data, when we find the x value is 0, we immediately see the y coordinate of the y-intercept. And in our situation, that would be 0, 5, 10. Visually speaking, you're going to look at the y-axis and see where is the point that's on it. And that's the y-intercept. But what's this information? Well, remember, x represents miles, y represents cost. So the cost to take a 0-mile taxi ride is $5.10. Maybe a better way to say it is the cost to climb into a taxi cab is $5.10. All right, so how much more will we pay for a 3-mile ride than a 2-mile ride? Well, what we could do is take the charge for a 3-mile ride, which is $12.90, and subtract from it the charge for the 2-mile ride, which is $10.30. But we could also think back, how is this defined? We were told that the cost per 1 mile is $2.60, so we know exactly what this subtraction is going to be. It's that $2.60. All right, then we're like, hey, how much more will we pay for a 5-mile ride than a 2-mile ride? Again, we could just grab from our table the cost of a 5-mile ride, $18.10, subtract from it the cost of a 2-mile ride, $10.30, and that gets us our results. But we could also think, I know 1 mile costs $2.60. There's a 3-mile difference between these. So 3 times $2.60 is the amount we're going to be charged, or the cost differential, if you will. Either way you want to calculate that, the result is $7.80. You pay that much more for a 5-mile ride than a 2-mile ride. All right, now we get a little tricky. So our author says, pick any 2 points on the graph that you drew and subtract the second coordinates. What he's referring to here is the y values. So I'm going to pick the last point, 5, 18, 10, and I'm going to pick this coordinate, 2, 10, 30. Pick any 2 you want. Pick some different ones if you're following this, if you're doing the work yourself, and see what you get. Now we're told to subtract those coordinates, so I'm going to do the small number from the large number. I learned about positive numbers before I learned about negative numbers, so I prefer positive numbers over negative numbers. Now, the historical development of numbers was the same way. Positive numbers came first. Okay, so I get $7.80. Then would you divide the result by the difference of the first coordinates for those same points? So what he means here is the x values. All right, since I did this y value minus that one, I need to do the same subtraction. So I'm going to do, this was the y's, the x's, I'm going to do 5 minus 2, which is equal to 3. And now we're going to divide this. Any guesses what we're going to get? Oh, you know what we're going to get. It's $2.60, right? The cost of traveling 1 mile. This is the slope. So our author tried to trick you into developing the slope formula. Here's what it looks like. Take a y coordinate, subtract from it, take the y coordinate of 1 point, subtract from it the y coordinate of another point. Take the x coordinate of the first point you chose, subtract from it the x coordinate of the second point you chose. That's your slope. I like to write this as, in the physics notation, delta y over delta x. That delta, that Greek letter delta, means change. So if you think what happened up here, we calculated the change in y between these 2 points as being $7.80. And then we calculated the change in x as being 3-unit change. When we divided this, we get the average change, or the change per 1 unit. And if we include the units here, it was miles in the numerator, or sorry, dollars in the numerator. It's miles in the denominator. All right, so we have one piece of a linear equation, that is the slope, which is the constant addition that we found in 2-1. So the number that you're adding each time in a sequence of numbers, that number is called the slope. Okay, let's keep going. So we're going to estimate the distance of a $16 cab ride. Now we're told to use either the table or the graph. So I'm going to switch to Desmos, where I have both the table and the graph. And if I were to do it from the table, I would note that after 4 miles, we were charged $15.50, and after 5 miles, $18.10. So it's between 4 and 5 miles, the cost of a $16 cab ride. And in fact, it's going to be closer to 4 miles than 5 miles. So I'm going to guess like 4.2 miles. Graphically speaking, it's a little more challenging to figure that out because we don't actually have numbers here, but it's a value in between 4 and 5. You can note actually that this line here is 16. So whatever this is, we could try to, we've got 1, 2, 3, 4, 5 tick marks. So we're dividing each of these as what, 1? So from the graph, I might think it's 4.1 miles. Note that this is an X value we were estimating. Now it says estimate the cost of a 2.5 mile cab ride. So we're about to estimate a Y value. The units on Y values are dollars. And again, let's jump back to Desmos. We're looking for 2.5 miles driving, so it's halfway between 1030 and 1290. So here's what I'm going to do. I'm going to take 1030 and add half of the change. Remember the change was $2.60? So I'm going to add $1.30, and I'm going to guess that it is what, $11.60 will be the cost of that 2.5 mile cab ride. I'm not writing down the explanation because I said it for the sake of time here. Okay, number 7. So we know that the cost of the cab ride is going up by $2.60 for each extra mile. Well, each mile beyond 0. So how much would you pay strictly for mileage if the ride is 10 miles? Note we're ignoring the $5.10 at the beginning. Well, it's $2.60 for each mile. We would add this together 10 times, or the shortcut for addition is multiplication. It would be $26 for those 10 miles. Well, if again we're just doing mileage, what about if we went X miles? So what if we didn't know the amount and just wanted to have an expression that told us the cost? Well, we're going to replace this 10 with an X. In the math world, we tend to write the letters second. So this would be an appropriate way to write it. You could write it before in front of it, like X 2.6, but that looks really weird to me. It is technically correct. You can also use parentheses, 2.6 parentheses X, to show multiplication. What you shouldn't do here is use the X that you were taught in elementary school, because this X now represents a placeholder for a number, and that number is an amount of miles. Okay, so the big question is, what do we do with this initial fee? Well, if our cost initially was $5.10, regardless of the amount of miles we went, we would add that then to the 260 times however many miles we've traveled, and that's going to give us the cost. Notice we're told to write that as equal to Y. We're calling Y the cost. So we now have a nice equation, and we can solve this equation for our 16-mile cab ride. By the way, notice that we could write this equation as Y equals 2.6x plus 510. Same exact equation. We wrote the numbers in a slightly different order. And if you're not confused yet, let me show you another way we could write it. You can write the Y value on the right side. All of these are the same representation. The reason, of course, with the rearranging the order that we add things is when you add values together, it doesn't matter what order you add. 3 plus 4 is 7. 4 plus 3 is 7. That's it. Okay, so how would we use our equation to check the estimate of a $16 cab ride? Well, notice that value of $16 is a y value. We're going to plug that into the equation and solve. Okay, here comes algebra, right? This is, you first encountered this in Algebra 1, maybe some 8th grade math. The goal is to get x by itself, so I'm going to subtract 510 from both sides. Oh boy, what does that turn out to be? 16 minus 510 is what, 1090? And then I'm going to divide both sides of the equation by that 2.6 so that I get a 1x. So we've got 1090 divided by 2.6. I don't know what that is. Equal to, I've got a calculator here. I'm getting, oh man, I was really close. Look at that. This is approximately equal to 4.192307692 miles. All right. Well, all those numbers are not necessary. Why don't we just round this to the nearest tenth of a mile, 4.2 miles. Okay. Then we're asked to, well, how could we check the cost of a 2.5 mile ride? Note this 2.5 miles is an x value. This is a little simpler because we just plug the value in for x and evaluate. We don't have to solve for anything. So 510 plus 2.6 times 2.5 equals 1160. We were exactly correct with our estimate. Turns out there's a nice way to use Desmos to solve both of these equations. So let's go check that out. In Desmos, I can type in the y equals 5.10, we don't need the 0 really, but I'll put it in, plus 2.60 times x. Hey, look at that. The line passes through every single point. That's perfect. Now, we wanted to know when, or for what x value, does y equal 16. So I type in y equals 16, and you can see this green line is intersecting the blue line at the exact value we found when we did the algebra. Hey, guess what? I don't care how you find it, just that you know how to find it. If you like this graphical approach, do it. Don't solve it by hand with that algebra. This might be faster. Okay, well, the other one we needed to know was what was the cost when x was equal to 2.5. So I plug in x equals 2.5 into Desmos as my graph, and where it intersects the blue line is exactly the cost. Again, I don't care if you about the algebra, as long as you can find the solution and understand what you found, that's what's important to me. In fact, I would almost rather you be able to do this graphically than algebraically. I think it's more powerful that way.